So here's all you have to know about databases to at least understand some of this talk. So in 1970, Ted Codd wrote his pioneering CICM paper. Basically, it had 2 points which were completely revolutionary at the time. First one was all data should be stored in relations, tables, simplest possible data structure. And the second one is, and it should be accessed in a high-level language, think SQL. And these were just completely contrary to the existing traditional wisdom. So it immediately incited a huge amount of discussion. And during the 70s, there were 2 prototype systems that were built that sort of embodied Ted Codd's ideas. The first one was System R, which was built at IBM Research, now at the Almaden Research Center, and Ingress, which was built by a pickup team of folks at Berkeley. So they're the 2 prototypes that are available as prototype systems in the 70s. With that, the land sharks are on the Squawk box. The subtitle is Why Riding a Bicycle Across America and Building Postgres Have a Lot in Common. We start in the summer of 1993. Illustra, which is the company commercializing Postgres, is down to fumes. And it falls to me to try and raise more money from our venture capital backers, who I affectionately call the land sharks. The only problem is I'm at a family event in rural Maine, in fact, at my brother's fishing cabin, which you see on the slide. I'm in fact, this is before the day of cell phones. Even now, cell phone reception, it doesn't exist at this place. So I'm on a landline, which is connected to a wall phone, dangling the cord into the bathroom where I'm trying to negotiate a deal. Negotiating with the VCs is really a challenge. First of all, they're on the Squawk box, meaning on a speakerphone, and I'm in the bathroom trying to yak with them. The conversation is depressingly familiar. They say more money, lower stock price. I say less money, higher stock price. Eventually, we reach an agreement, and Illustra will live to fight another day. This talk intermixes 2 different episodes. The first one is the design, construction, commercialization, and ultimately sale of Postgres, which occurred from the early 80s to the mid-90s over that 12-year or so period. The second one is a bicycle ride that my wife and I did across the country in the summer of 1988. Both of these start off on a real high. Here we are at the ferry terminal in Anacortes, Washington, in early June of 1988. We are about to start riding east up the North Cascades Scenic Highway. Our destination, some 3,500 bicycle miles away, is Boston. We are in very high spirits. It doesn't faze us that we have never ridden a tandem bicycle before. We're equally unfazed by the fact that the longest bicycle trip we've ever done has been 5 days, and what we're facing now is at least an order of magnitude more. We are not daunted by the fact that we have never climbed mountains like the ones directly in front of us. And also, we are undaunted by the fact that we have an 18-month-old daughter who you'll meet in a couple slides, and she's going to spend the summer on the road. We're in very high spirits. We're setting off on a great adventure. In Berkeley in 1984, well, as Barzan said, I built Ingress, and The commercial company was started in 1980. The commercial code line is now 4 years old. And of course, wildly better than the academic code line that we're still working on and prototyping with. And it makes no sense whatsoever to continue doing prototyping on our code line. That's just a silly thing to do. So it's really tough, but we push the code off the cliff and start something new. So what is Postgres to be? Well, the first thing that it's going to be is something called abstract data types. So SystemR and Ingress were completely focused on business data processing data. That was pretty much the dominant database market at the time. And also, we were focused on out-IMSing IMS, out-codicilling codicil, which were the dominant alternate proposals. So, and they were entirely in business data processing. So Ingress and SystemR were focused on business data processing. And by the way, they were no good at much of anything else. So by 1984, there were quite a collection of papers of the following template. This relational stuff is supposed to be really good. So I tried it on my favorite problem, X. Think library information systems, think computer-aided design, think geographic information systems, ... So we tried it and it didn't work worth a darn. So our solution is to add Y to the relational model. And to me, it was really clear that you started out with something that was clear, simple, and easy to get your arms around. And this was going to be death by 1,000 cuts. So you start adding a whole bunch of warts to the relational model. This was clearly going to be a disaster. So what was the problem? The problem is that in business data processing, everything is character strings, integers, floats. But that isn't true when you get to other stuff. So let's look at a very simple example from geographic information systems. So let's assume that we have employees, say Sam, make him 38 years old. And let's suppose we are going to record the geographic coordinates of the property that his house sits on, just say. And suppose it's a rectangle. So there are 6 fields in an employee record, name and age, and then the four numbers that are the 4 corners of his property. So then if you are somebody who's looking for variances in building permits, so if you want to have a variance, you've got to notify everybody that's within a certain distance of the property where the variance is to be located. So that's basically find me all the employees who overlap some specific rectangle, which take the property in question, grow it by a certain amount, and that gives you a bigger rectangle. So you want to run this query. And this might be the carpool program. You can think of a lot of examples that this is basically representative of. Well, one of my favorite things to do is to ask students, code this query in SQL. And it turns out that what's at the bottom of the slide is correct. Some of you will tell me it's not, but I promise you it is correct. It's not exactly obvious why it's correct, so this is kind of messy. Also, this is the best way from a whole bunch of others to express, This is the best way to express this query from a whole bunch of others. There are lots of other much more messy representations. So this is messy and very difficult to optimize. And you just sort of look at it and you say, there's got to be a better way to build a railroad. And so, of course, there is. If you get rid of the idea that you're restricted to character strings and numbers, what I'd really like is I'd like a data type called box. And so I really want to have 3 fields, name, age, and location. And location is of type box. And the bits that are in the location field are some representation for a box, and I don't really care exactly what it looks like. But if I have 3 fields, then I express the query. I want to find the names where location overlaps, make a box out of the coordinates of the thing I'm interested in. So it's now pretty obvious that that's correct. And all I need to do this is user-defined data types. Let there be whatever data types you want, not necessarily just strings and numbers. Let there be user-defined operators, because what you want to do with boxes is completely different than what you want to do with strings or numbers. And then I need user-defined functions. In this case, I want to make a box out of 4 numbers. So all I want is to be able to add new types to a database system. And I didn't invent this. EL1 did this a decade earlier. So all I needed to do was personalize this to what a database engine actually needs. And that is adding a bunch of code, think C++, to a database engine and then calling them at the correct time. So that's really what you have to do. And of course, the problem is the concept is simple and easy and powerful, and the devil's in the details. The problem with the details is we've got indexes. Database systems had them at this point for years, B trees and hashing. So you want to be able to use B trees on the box data type. So that means you've got to be able to linearize boxes, because B trees demand a sorted set of lists. You've got to be able to have new indexes, because in the geographic information system space, things like R trees are very, very, very popular. Although they were invented in the 80s, different kinds of indexes are appropriate for different kinds of data. So you've got to be able to add user-defined indexes to a database system. You've, of course, got to teach the query optimizer how to optimize all this stuff, and that's considerably messy. Database systems have commutativity rules, which is you can interchange not and, for example, although that isn't one of them. You've got to be able to use commutativity rules on new types and new kinds of indexes. Database systems insist on optimizing not. So if you say not age less than 20, any database system will convert that into age greater than or equal to 20. So there's a whole bunch of twiddles and optimizations that you need to extend to work for new types. So anyway, we were going to focus on abstract data types and figure out all the details in this kind of stuff. Okay, back to the bike ride. Here we are in Winthrop, Washington. I'm standing next to Marianne, who is our driver and babysitter, along with our daughter Leslie in her stroller. I can just barely stand up at this point. Our day started in Devils Lake, Washington at 5 a.m. For the next 8 hours, we rode uphill. Telephone pole by telephone pole, we struggled 5,000 feet into the Cascades. Over the course of 50 miles, it got really cold. We put on every piece of bicycle gear that we brought with us. Then it started to rain. Then it started to snow. And of course, bikes don't have snow tires. So finally, cold and tired and wet, we arrive at the aptly named Rainy Pass. And here we are at the top of the pass, sort of celebrating that we made the first pass. Then after a small downhill, we have another 1,000 feet to climb to the top of Washington Pass. And here we are, now super exhausted. Of course, after that, there's a glorious downhill into Winthrop. The net effect is that we are dog-tired, but we are elated. And we're elated because there's a whole bunch of passes in front of us, but we're over the first two. We proved that we can do the mountains. Chris Date wrote a pioneering paper on referential integrity. Basically, this was what to do with what's now called foreign key primary key constraints. Well, what's this all about? Well, suppose you have our two favorite tables, a table of departments and another table of employees. So I have a shoe department and I have a candy department, and I have 4 employees, Bill, Art, Sam, and Tom. And kind of the question to ask is, suppose somebody comes along in SQL and deletes the candy department. So there used to be 2 records in the top table, and now there's only 1. So notice that if you look at Art, in Art's record, there's effectively a pointer to the candy department, which is now gone. So there's a dangling reference. So what do you do with a dangling reference? So Chris Date had a bunch of solutions. The first is replace Art's record, the candy cell, with null. If Art used to be in the candy department doesn't exist. He's now in the null department. Second thing you can do is cascade the delete, which is delete the candy department and delete every employee that used to be in the candy department. So that basically fires everybody who used to be in the candy department. Third option is just refuse the delete, saying this is going to leave you with a database that's in an inconsistent state. Refuse it. So these 3 actions all will create a consistent database as a result of somebody trying to delete the candy department. So Date said, let there be all possibilities. And of course, if you do an insert, there's 3 corresponding solutions to return that database to a consistent state. So database folks are really interested in consistency, as you can imagine. And so Chris Date's solution got a lot of traction. Commercial systems at this point started to put referential integrity into their engines. The problem was, in effect, you're looking at a little rule system. You have to do the right thing. When the user does something, you have to do something else. And so you need a little rule engine to do that. Well, around now, there were a whole bunch of other little rule systems that people were proposing. So there were a bunch of proposals to do triggers, which is to say, if I do a salary update to Sam, make sure that Bill gets the same update. So cascade the update. So triggers were a proposal on the table. That requires another rule system. Integrity constraints were something proposed by Mike Stonebraker, which is salaries must be non-negative, stuff like that, yet another rule system. So there's starting to be a bunch of ideas that required rule systems. So I said, we're going to die if we implement all these special purpose rule engines. Let's have a single mechanism that does all the kinds of rules that you want to implement. Now, about now, the 5th generation Japanese computer proposal was going on, which said code the world in Prolog. And rule systems were all the rage in the AI community. And so all of us were looking at rule engines, if-then rule engines. of the flavor of conniver and planner prologue style stuff. So I really hate rule engines. I hate them with a passion. And the reason is they have really horrible semantics. So suppose you got two rules. Make sure that George is in the shoe department. That's rule number one. Rule number two is move everybody over 40 from the shoe department to the candy department. Perfectly reasonable pair of rules. So let's suppose you execute them in the order they appear on the slide. So make sure that George is in the shoe department, so he gets put in the shoe department regardless of what department he's actually in previously. Then, assuming he's over 40, we'll move George from shoe to candy when we implement the second rule. He ends up in the candy department. Let's suppose I reverse the order of the rules. So he's over 40, regardless of what department George is in, we move him to the candy department. Then we execute the first rule, which is put him back in the shoe department. So depending on the order in which you implement the rules, you get a different result. That drives database folks crazy, that the net final state of your database depends on which order you run the rules in. This is made worse by SQL being a set-oriented language. You can update a whole bunch of records, and then if the rules take over, you get a huge mess. So the first problem is it has really awful semantics. The second problem is if I handed you a 20-line prologue program and said, what does this program do? I guarantee you wouldn't be able to figure it out easily. So rule systems as a notation are just impossible to understand. So I hated this stuff with a passion. So that was not the right solution to getting this single system to work. So my solution was fairly pragmatic, which is to say SQL has updates. So if I want to update Bill's salary to be the same as Sam, well, there's the update command in the middle of the slide. That will set Bill's salary to be the same as Sam's. Suppose I add a single keyword, always. And so any update can be tagged with always. What that will do is it will appear as if the command is perpetually running. So take any update and just make it look like it's perpetually running. So this has somewhat cleaner semantics than an if-then rule system, and it seemed like an interesting thing to explore. Here we are at Marias Pass, Montana on day 15. Sort of Beth and Leslie and I on our bicycle. This is the Continental Divide. The endless climbs in the Rockies and the Cascades are all behind us. We can look forward, out of sight to the right of the slide, and you can see the Great Plains stretching out in front of us. The interesting thing to note is it's downhill to Chicago. And we are absolutely elated. We are done climbing the mountains, and we are in a very, very, very good mood. Okay, the third idea that Postgres had was all database systems have to do crash recovery, which is anything bad happens, you've got to make sure that all transactions that were in flight at the time of the crash are either finished or backed out. You've got to leave the database in a consistent state. Well, the traditional way to do that is you have a database system that's managing the database, which is this thing on the left. That's what you think of as the data. But in fact, there's another database system that the database system is also managing, which is the log. Every time you do something, you write what used to be in the log plus what's going to be in the log. And then if something bad happens, you look in the log and you figure out what to do, and you can recover the database by processing the log in fairly complicated ways. The problem is you've got two data stores. You've got the log and then the data. And they have to be very carefully synchronized or all hell breaks loose. And the log code that processes the log if there's a failure is complicated and really ugly. And by the way, it has to work reliably every time for sure. And it's a little difficult to tell a database system why you fail about now so I can test my recovery code. So it's ugly code, complicated, and has to work perfectly, and very difficult to test. So as computer scientists, you all say, this sounds like a stupid way to run a railroad. Why don't we try and do something better? So the Postgres idea was, suppose instead of updating Mike Stonebraker's salary and changing the record that was there and producing a new one, and therefore you have to write the old version into a log, why don't you just leave the old record there and write a new one with his new salary? This is what's called these days no overwrite storage, and it's becoming a lot more popular. And Postgres sort of decided to exploit this, in the 80s. The idea is that the log and the data are all in one database. There is no separate database system to be synchronized, and you simply write the new values, leave the old values where they are. This gets rid of crash recovery code and makes the database system a lot simpler. And if you keep the old values around for a while, you can provide time travel. So you can ask, what was Barzan's salary a month ago? And unless the database system decides to get rid of the old stuff, it's still there. So you get time travel, you can sort of adjust time and run historical queries. So this sounded like a good idea. Of course, like everything else, the devil is in the details. The problem is that in the traditional world, the log is write optimized. What you do is you write records to the log. You make sure that that's very nice and sequential. The data is organized to be read optimized so that you can read it fast. It's indexed. You use clustered indexes, all that stuff. So you've got two different databases, one write optimized and one read optimized. You're going to run these things together, and it's going to be tricky to try and make this competitive. It's going to be a interesting placement problem to try and make this work well. So that was what we took on. So the Postgres game plan was to say we're going to bet on abstract data types. That's going to do things like geography well. We're going to have a single rule system using this always command. And we're going to bet on no overwrite storage. Postgres had a bunch of other stuff in it, but this was the major pieces of Postgres. So that was the game plan circa 1984. That was the game plan we set about executing on. Well, in both of these endeavors, they started off on a high, but things don't always go very well. So things got bad in both of these projects. So let's start with the bicycle ride. So here we are in North Dakota, entering the state. North Dakota is horrible on a bicycle. Basically, what you do is up ahead about 10 miles, you see a grain elevator signifying the next town. You ride toward the grain elevator for an hour. You get into the town, you go through it in a couple minutes, and up ahead, you see the next grain elevator 10 or so miles away. It is monotonous, it is bleak, there are no trees. My wife and I joke with each other that the state tree in North Dakota is the telephone pole. But that isn't what's killing us. What's killing us is that on the Great Plains in a bicycle, you're supposed to be able to just sit up straight in the saddle and get blown across the state by these howling winds that are on the Great Plains. So we were expecting to be blown across the state at 16, 18, 19 miles an hour. Well, the wind was howling all right, but it was howling from east to west. We were riding straight into a gale force wind, and we were struggling to make 7 miles an hour. So this, after 3 or 4 days of this, we're really getting depressed. And it comes to a head in a little town called Drake, North Dakota, about halfway across the state. We were exhausted as usual, and we've ridden about 50 miles, and we just can't go any further. Our objective was to get to Harvey, and it's still 25 miles away. We're not going to make it. Moreover, it's still 250 miles to the tree line and the Minnesota border, and we have no idea how we're going to get there. Well, after all these interesting ideas in Postgres, reality set in 86, 87. We had decided to code Postgres in Lisp. We'd coded Ingress in C. We didn't want to do that again. C++ wasn't ready. Ada wouldn't have worked out very well. So we drank the AI Kool-Aid and started implementing in Lisp. This was a disaster. It was like 3 orders of magnitude off of what it had to be. So as soon as we figured it out, all the code went over the cliff, and this was the first of many rewrites. The abstract data type system is a high point. It works really well, or it appears to work really well. And what made me figure this out was I was associated with the commercial Ingress guys, and I got a call from an Ingress customer right around the time when Ingress released date and time as a data type. And so the customer said, "You implemented date and time wrong." And I said, "Oh, how so? You know, we implemented the Julian calendar. You can subtract two dates. March 15th minus February 15th is 28 days, except during leap years, except during double leap years." What do you mean we implemented it wrong? What he wanted was he was computing interest on financial bonds. And for whatever reason, the way it was done in his shop was that you got the same amount of interest during every month, no matter how long the month was. So he wanted a calendar year, to be divided into 12 equal length months, each 30 days long. So to him, March 15th minus February 15th was 30 days. Thank you very much. His question was very simple. He said, why can't I overload subtraction of times to work the way I want them to work? And of course, Ingress wouldn't let you do this. But this was child's play to Postgres. You just needed a financial bond data type, and it would have worked great. We're having a lot of trouble with time travel. It's a great concept, but it's tricky to tune and make it performance competitive. And our rule system basically doesn't work. I had said the objective is we've got to be able to do all 6 cases of Chris Date's referential integrity. If we can't do that, we're nowhere. And I couldn't figure out a way to do it. So a lot more code goes over the cliff, and we go back to exploring a more conventional rule system. So over the next 3 years, my colleague, the wine connoisseur, and I spent a lot of time on what to do about time travel, what to do about rules, how complex can complex objects be. Think of this as a 3-year slog through the swamp. Not very much fun, with the end of the tunnel always elusively distant. Well, bad times don't last forever in either of these endeavors, so back to North Dakota, where we left ourselves in Drake. We're now in Carrington the next day, and serendipity intervened in a really big way today. No, it isn't the wind. The wind is still howling right in our face. It's my brother, shown here in the slide. He flew out with his bicycle. Marianne picked him up at the Minot Airport yesterday afternoon. He is very, very strong, and he is fresh, not beaten down by the North Dakota winds. So today, he let us draft behind him like they do in the bicycle races. And so for 82 miles from Drake to Carrington, with a cadence of faster, slower, we try to stay 3 inches behind his rear wheel. And against the horrible wind, we made 82 miles. What's really clear is that we're over the hump. We're going to get out of North Dakota 3 inches behind my brother's wheel, if necessary. So we are elated, albeit exhausted. Well, we finally get Postgres to where it pretty much works. So in the DBMS field, the ultimate arbiter of good ideas is the commercial marketplace. So you want to make a difference, you've got to get your ideas into the marketplace. There are exactly 2 ways to do it. Convince some big company to use your ideas and put them in their code line. We had a course, the commercial Ingress guys were right there, so they were certainly an obvious choice. But of course, they had their own agenda. And in fact, there's a fabulous book called The Innovator's Dilemma, which you should all read, by Clayton Christensen. Basically, it says that if you're the commercial market leader with obsolete technology, it is very difficult to morph to the new stuff without losing your customer base in the process. And so big companies are not very receptive to new ideas in general. So a much better idea is to just start your own company. So that's exactly what we did. I recruited Mom and her husband, the short one. EMP1 and Quiet 1 came over from the academic team, joined shortly thereafter by another member of the academic team, who I'll call Triple Rock. I recruited the tall shark as lead venture capitalist and interim CEO. And we had money. We were off and running, converting the query language from Quell to SQL, hardening the code, improving performance. In the honeymoon phase of any startup, it's a real high. So both projects are on a high. Here we are, sort of not very far from right here, in a place called Luddington, Michigan. We've just wheeled Boston bound off of the Lake Michigan ferry, and we're starting to ride southeast through Michigan. It's a real uptone feeling. We are now less than 1,000 miles from Boston, and it looks like we're actually going to make it. The commercial company, after a couple of miscues, we were named Illustra. We managed to recruit the first few customers. They're called lighthouse customers. We raised some more money when we ran out of money. Remember slide 1 in rural Maine. We hired a real management team, the voice of experience as CEO, Uptone as vice president of marketing, and Smooth as the sales guy. We have a real management team. We have money. We have the first customers. The future is looking up. So life is good in both of these endeavors. Of course, it doesn't last. So both of these endeavors hit another low fairly quickly. Here we are in Ellicottville, New York, day 49. We've been lulled into complacency by the flat ground in Michigan, Wisconsin, Ohio, Minnesota. And we hit the Allegheny Mountains. The trouble with the Allegheny Mountains is that you are up and then down the same 500 feet over and over and over again. It is really exhausting riding. What's more, in the hotel that we stayed at last night, it had marble floors in the hallways, and in my bicycle cleats I slipped and wrenched my knee. So there are only 3 legs pushing Boston down forward. But the biggest problem is the hills are just really hard. So I look. This is not me. I won't touch it. So I look for the innkeeper in the inn we're staying at in Ellicottville with a very simple question. How do we get to Albany without climbing all these hills? Well, in Berkeley, out of thin air comes our first horrible crisis. We were basically selling ADTs. You want to do geography, we can do that. You want to do financial bonds, we can do that. And by and large, that message resonated very well with the first few lighthouse customers. However, after that, the more cautious customers said, well, this ADT idea is a really good one, but we don't want your geographic type library. We'd written one. We want geographic types from the large GIS guys, people like ArcInfo and MapInfo. So the customers wanted ADTs from the app vendors. So we made a pilgrimage to Redlands, Washington to talk to Jack Dangerman, who's the CEO of ArcInfo Corporation. So we said, we have this great, fabulous database system. You want to take your geographic types, stick them into our database system, and life is going to be great. You're going to make a huge quantum leap difference in how things are going to work. He looks at us as if we're crazy and asks us a very simple question. He said, how many customers do you have? And we'd say, well, about 15. And he said, well, come back when you've got 500. So we were up against the following catch-22. The customers wanted ArcInfo and other like type libraries. The app vendors, like ArcInfo, wanted a distribution channel, which is they wanted customers. So the customers wanted the app vendors, and the app vendors said, we're not interested until you have some customers. So this is a catch-22, and we're sitting there saying, oh my God, what do we do now? Well, of course, sales were not going very well, as you can imagine, so we ran out of money again. And since things are not going well, we got the dreaded down round. Now, the whole idea behind a startup is you raise some initial money, you do good things, you get to another milestone, you get to raise money at a higher valuation and repeat. Well, that all assumes that things are going well. So in this case, things were not going well. And so the VC said, well, you're not worth as much as the last round. We'll put in money, but at a lower price than last time. This generates 2 problems. The first one is, of course, dilution, because you're selling stock at a lower price. But the second one, which is even more insidious, is that you've got to reprice the previous round down to the new price, because that's in the fine print in all of these agreements. So you get a double whammy on dilution. So, of course, the employees, me and the people who worked for Illustra, said, well, you're diluting us off the face of the earth. We're not going to continue. Have a company. So what ends up happening is a zero-sum, ugly 3-way negotiation between the old investors, the new investor, and the employees as to who gets what in this company. Ugly, ugly, ugly. This is a fate worse than death. If you can ever avoid this, avoid it. So about 3 months go by with this ugly negotiation. Finally, we reach an agreement. The percentage of the company that the various VCs own changes very slightly. The employees largely get made whole, and we finally get back to work. Well, bad times don't last forever. We found good times again. So the innkeeper in Ellicottville offered us very prescient advice. This would have been something obvious to somebody like Robert Fulton in the early 1800s. The innkeeper said, ride straight north to the Erie Canal and hang a right. And that's what we did. And after a pleasant but hot and flat cruise down the Mohawk Valley, here we are in Troy, New York. And we are now up against the last hill. This is a well-known bicycle concept. This is the last hill before you have to climb before you reach home. The last hill is, in fact, on the pavement in Wildcat Canyon Road in Orinda, California. It's on the route back to Berkeley, and it is the last hill you have to climb before you get back to Berkeley. We are up against our last hill. All we have to do is climb the Berkshires to Pittsfield, and then it's easy going to Boston, now only 186 miles away. Well, serendipity intervenes in Illustra in a really big way. And again, this is out of right field. So we're up against this catch-22. So what happened next was the internet is taking off. This is the time Bill Gates goes to Cornell, discovers that the internet is a big deal. And so that's all ancient history to you guys, but it was a huge deal at the time. So our marketing guy, Uptone, turns the company on a dime. We are no longer about abstract data types and GIS or any of that stuff. We are the database for cyberspace. If you haven't, the internet is taking off. You need a database system for the internet. At the time, there was a project which is a bunch of photojournalists putting up a web page every hour with a whole bunch of stuff in it. And Illustra was the database for this thing called 24 Hours of the Internet. We got a lot of buzz, got a lot of sales leads. And in fact, one of the major internet vendors of the time invited us to a bake-off against, of course, the traditional elephants to be an embedded database system for his product. This would have been a company-making transaction. Maybe we've turned the corner. Life is looking good. Of course, that doesn't last long. Instead, this internet bake-off, instead of this company trying out a GIS query or something like that, he said, well, inside every sort of complex data problem, there's a business data processing problem inside it, and we're going to try out that first. So his benchmark was basically standard transaction processing, which the relational database vendors by now are very, very good at. And we, of course, are not good at. We'd never tried to optimize TP performance. We do transactions, but it's not in our wheelhouse. My stomach just sinks. It's clear we're going to lose this benchmark and lose it by at least an order of magnitude. So we're sitting there saying, now what? If we have to improve transaction processing performance, that's going to be at least a year or two, and it's going to be a lot of hard work. And how are we going to pay for it, et cetera, et cetera. Well, I'm now up to telling you the end of both of these tales. So getting Boston-bound into downtown Boston, let alone finding a place we could actually get out to the water to actually finish, Any of you who've been to Boston know that isn't something you want to do. So we choose to aim for Wollaston Beach, about 10 miles south of Boston. After the ritual of dragging our bike across the sand and sticking its front wheel in the water, here we are done. We are now adjourned to the bar at the edge of the beach, drink a glass of champagne, and decide what comes next. Of course, serendipity intervenes in this benchmark again in an unexpected way. One of the elephants that we had been competing against in this benchmark is so threatened by the fact that the internet is going to have all of these other kinds of problems and they're no good at any of them. So he decides to buy Illustra. And this solves all of our problems. First of all, he has a transaction processing engine into which we can stick our stuff. That solves our TP problem. He also has a lot of customers, so it solves this catch-22 problem. So we set about, we say, great, we'll sell ourselves to you, and we set about putting Illustra features into their system. So what should you get out of all of this yak? Well, first of all, why would I tell you a bicycle story? So, since you're all computer scientists, here's an algorithm for riding a bike across the United States. Until you get to the ocean, get up in the morning and ride east. And persevere and overcome whatever comes up. And if you keep doing this long enough, I guarantee you, you will succeed in riding across the country. Well, let's abstract this a bit and say, well, until you reach a goal, whatever that is, get up in the morning and execute an appropriate action and persevere and overcome whatever obstacles come up. So this now is a general purpose way to get to some goal. Let's make this into a macro. And the macro is make it happen. Whatever comes up, make it happen. So why would anyone want to ride a bicycle across America? It is long and hard. I guarantee you it is long, and I guarantee you it's hard unless you were an Iron Man. There are periods of depression, there are periods of elation, but there's lots of monotony. North Dakota is not fun. And so there's a lot of slog through the swamp. So why would anyone in their right mind want to do this? Well, if you look at my career, so I hung out at Michigan, not in this building, it didn't exist. I got a PhD. Getting a PhD is by and large not much fun. There's a lot of hard work, there's a lot of monotony. Getting your code to run is monotonous. I failed my qualifying exam the first time. That was kind of a downer. But mostly what it takes to get a PhD is make it happen. And so in my case, it was 5 or 6 years, and that got me a PhD. Then I went to Berkeley as an assistant professor. Your immediate goal is now get tenure. And getting tenure is a lot of hard work, a lot of monotony. Periods of elation, your paper gets accepted. Periods of depression, your paper gets rejected. Mostly it's make it happen for another 5 years or so. Riding across the country, well, it's make it happen for 2 months. So you can draw the obvious conclusion. So I have a makeup where I obviously look for stuff for which make it happen is the answer. And that's why I would choose a bike ride. Building Postgres is essentially the same thing. You have to have a good idea. You then make it happen for a prototype. That's a lot of hard work with a lot of depression, a little bit of elation, and a lot of monotony and slog through the swamp. Then you have to start a company, hire some people, hire execs, and then you have to make it happen for another 5 years or so. So basically, building Postgres was have a good idea and then make it happen for a decade. why would anyone in their right mind want to do this? It is just too hard. So I think you can form your obvious conclusion. It's more of Mike Stonebraker has make it happen on the brain. Now I'm always asked, where do good ideas come from? I've never had any good ideas by communing with nature on the mountaintop or going out onto the Huron River or whatever. I've never had any good ideas that way. Instead, they all have come by talking to users, then talking to some more users, get off campus and talk to people with real problems, and then hang around a critical environment of smart people, and there are lots of them around, like here and MIT and Berkeley. So I recommend talking to users, get off campus, use shoe leather, find out what people actually want to do, and then try and solve their problem rather than making up your own version of what you think their problem might be. I have a bunch of ideas on what I think is important, what I think isn't important. There's a test of time talk in ICDE 2015. Go look at that. That's what I thought as of last year. Where does make it happen come from? I think if you don't have make it happen, you're going to have a really hard time getting a PhD. Where does it come from? I don't know. That's psychological stuff, which is way above my pay grade. What about serendipity? We would not have gotten out of North Dakota without my brother. Illustra would not have succeeded without Uptone's pivot and then threatening one of the large relational database vendors. Often is very significant, and it just, who knows when serendipity happens. There's also anti-serendipity, which is bad things can happen also. Present day, we still own Boston Bound. It sits in our basement gathering dust. It has not been ridden since Wollaston Beach all those years ago. I still love to take on physical challenges. Climbing all the New Hampshire 4,000 footers was one of them that I did recently. Illustra was successfully integrated into the Informix code base. It's still available. Postgres's ADTs have been added to almost all relational database systems. It's kind of just one of the things that you've got to have, table stakes. However, the biggest impact of Postgres, again, was pure serendipity, which is Jolly Chen and Andrew Yu converted the academic Postgres prototype to SQL, and it was then picked up by a pickup team of folks who have shepherded it ever since then for the last 20 years. The thing that you download today comes from the dedicated effort of a dozen or so pickup folks. This is open source at its finest. This group of people has nothing to do with me. And of course, Postgres code formed the starting point for a whole bunch of database companies, including Greenplum and Netezza. As Barzan said, I'm still building database systems. I talked today about Postgres. I could have used the CStore and Vertica experience. I could have used the HStore VoltDB experience. I could have used the SciDB Paradigm 4 experience. Each of them had essentially the same kinds of ups and downs, the same kind of make it happen for a decade. I could have used any of these for this talk, and I just chose to use Postgres instead. Postgres was written by 39 Berkeley students and staff. Here they are on this slide. Postgres would not have happened without all of these super smart graduate students and staff members. We would not have gotten anywhere post commercialization without some incredibly talented system programmers and some super competent startup executives. And also, without the land shark's money, none of this would have been possible. I want to finish with exactly 2 slides. First one is none of this would be possible without my wife and family. Here you see Leslie, 27 years later, on the right-hand side, and my other daughter, Sandy, and my wife, Beth. Beth not only had to spend 2 months looking at my back as we rode across America, but has to deal with my insane desire to start companies and my desire to make it happen. And I think she doesn't really realize that she's personally responsible for keeping me from falling off some of my own personal cliffs. And lastly, Jim Gray. Jim Gray was lost at sea 10 years ago. Jim was the 1998 Turing Award winner. He is absolutely a mountain of a man in the database field. Here he is hiking in the Sierras. I think I can say for all of the database community, Jim, we miss you every day. Thank you very much.